Hey, what's up, guys? This is John. So today, another Codeforce problem. So this one, Tokitsukaze, CSL, and Stone Game. So Tokitsukaze and CSL are playing a little game of stones, and so there are like n piles of stones, and each stone has like this some stone. Each pile has some stones, and the two players take turns to make moves. So Tokitsukaze moves first, and on each turn the player can choose an empty pile and removes exactly one stone from the pile. And the player loses if all the piles are empty before his turn, or if after moving the stone, two piles, possibly zero, contain the same number of stones. And supposing that both players play optimally, so who will win the game? So, and here there are some examples, right? So if there are like three piles of stones and where we have 2, 3, and 0. So if the Taki Tsukaze play first, so he can only like choose to remove the stone from either the pile 1 or pile 2, but but it, but if he choose the pile 2 here, right? So after removing pile 2, he will end up like with two piles have the same stones, which means he will lose. That's why the he will only uh, remove the stone from pile 1, right? And here are some like examples here, right? And so if the first person wins, we if this Toki Tsukaze wins, we print this word. Otherwise, we print that one. I mean, to solve this problem, actually, so all we need to do is that we just need to know like, so what is what are the cases that the player will definitely lose at the beginning, okay? And otherwise, each player will just play this game optimally. And so what's going to be the ending point? So the ending point is like this. So it doesn't really matter like how many stones we have for each of the for each of the pile. So let's say we have four piles. Uh, Besides the cases that the first person will always lose at the beginning at the first move, and in the end, right? In the end, the stones will eventually become to 0, 1, 2, and 3 because because at this point, whoever moves next will lose, right? Because if the remaining stones like they're increasing, right? If they're like increasing, so it doesn't really matter which pile next person choose. It will always end up with two piles that having the same stone. So if he choose like this one here, we'll have two zeros. If he choose two, we'll have two ones. Choose three, we'll have two twos. So here is the key observations we need to make. So that's the first observations. And the next one is that what are the cases that the first player will always lose. So I think there are like four cases in total. So the first one is what? The first one is if there are like two piles. I'm sorry, if there are two piles who have the zero, right? If there are like two zeros at the beginning, so it doesn't really matter what are the other piles, uh, what are the other piles of stones, because after the first move, we'll always have like two zeros left, which will make the player the first player always lose. So this is the first case. So two or more zeros. So that's the first one. How about a second one, right? So a second case is what? If we have like A, so I'm assuming A is the number of the piles. If we have like three piles that have like A minus one, A, and A. So this is always also like a definitely lose for the first person, because the if the persons, let's say they're like some other piles, because we already have like two A's, two piles who have the same stones, right? And to if he choose to remove any other stone, any other pile, so we'll end up like with these two piles with have the same A stones. But if he decided to break this pairs by removing either of these two piles, since we have A minus one here, we'll end up with like the two A minus one pile. So this is also like the a definitely loss, right? So we have A minus one, A, and A. And how about the next one? The next one is like it's A, A, and A. So this is also like a definitely a certain loss, right? Because with this AAA, similar like this A minus one, A minus one, no matter which one the uh, the persons choose to move, the first person will always lose. So and actually, so basically we're checking uh, the initial state, right? If the first person will lose after his first move. So that's the third case. And what's the last one? So the last case is like this. We have A, and BB. This is also like a certain a certain loss, right? Because we already have two pairs at the beginning. So no matter which pile the first person choose to remove, we always end up with another pair, right? With the same stones. And that's basically the four cases, the four initial state that the first person will always lose. If none of the cases is satisfied, then it means that in the end, since two players will both play optimally, in the end, the stones will always end up like within to this state. So, and then we know, right? So then we can check. Then we can check the moves until until this state. And we just need to check the parity of these moves here. If it's like, I think if the moves is even, then the second player wins. And if the moves is odd, the first player wins. And how can we check the moves here? Now this is like the increasing like sequence here, right? So we have a formula for this, right? So it's going to be n times n minus 1 divided by 2. So that's the total number, that's total stones left. And since we have the totals, right? It's just like we just need to use the total minus this one, so we can get the moves here. And then we just need to check the parity of these moves. Yep. So I think that's pretty much the idea here. Okay, so let's start the coding here. Mm, so to start with the coding here, we need some like variables. Let's say we have a n here, and then we have like we need numbers, right, for the stones. So that's that, and we also need like a map to store the count. So the count of the stones. So when we read the stones in here, we need to read everything in this like array first, and I plus plus I, right? So that's that. And we also need like total, right? So the total is like the total stones. So I'm going to use like sum s to add to represent the total. So total is we accumulate this the current stones, and we also can so basically this map here, the map here, it means that we want to store the frequency of the numbers for all the number of stones for all the piles. That's why I'm going to use this one to count the number the frequency of each number of stones for all the pairs, because we'll be using this count to calculate the pairs of the stones who have the same number, who have the same stones. Okay, and then I'm going to sort this list here, I plus 1 plus n. So the reason I sort it is because that will make it easy to find the a minus 1 AA and the a case. So, and the next one is we just need to check those special cases one by one. So the first one is the a minus 1 a and the a case, right? So we have for I int equals to 3 and I smaller than n, I plus plus, right? Since we're going to check the previously two state. So we just need to check the previously two uh, elements, right? So if the a I is equal to the a I minus 1 and a I minus a I minus 2 is equal to 1. If that's the case, right, we simply output CSL and B, and then we just return. Okay, so and the next one is it's the other three special case. So to do that, we just need to iterate the count map here. So we'll be using this one to check all the other cases. So we're gonna have like the iterator have um, we need to have like a pairs starting from 0, right? And then for the iterator start count dot begin, and the iterators not equals to count end, and then iterator plus plus. Okay, so if the iterator is second, right, the second one, since the the first one, so the first one is the piles, is the number of stones, and second one is the frequency of that number, right? So that's why we use the second one. If any uh, number has a frequency that's uh, more than 2, right? So this is like the AA case, basically, right? A A A case, and same thing. We do the same thing here. We just return this one, and it's A and BB case, right? So if the iterator, the second one, right, the frequency is equal to 2. So actually we're not checking here. We're checking two piles, right? Two piles have the same number of stones. So if whenever there's like a iterator that count where number is 2, it means that two piles have the same number, and then we just do a pairs plus. Okay, and once we have looped through the count, we have the pairs who has the pairs that whose like the number of stones are the same, right? The same, and then here we just check the two pairs, the A B case, and two zero case, right? So we simply check if the count of zero is greater than uh, uh, equal greater than 2. So 0 means that if we have 0 stones appeared more than twice, right? Then that's the two zero case, or the pairs is either equal or greater than 2. That's the AABB case. So again, same thing here, right? And here, right? So otherwise, right? Otherwise, calculate, right? Calculate the moves before reaching 0, 1, 2, 3 until n minus 1. So that's why we have the moves equals to what? The s, we already have the s minus what? N times n minus 1 divided by 2. And then we just output based on the parity. Moves divided by 2. If this one is 0, right? And then we just we output the this guy. Otherwise, and SJF Yeah, yeah, I think that's it. So let's try to run a few test cases here. And so we have 1, 0. That's this one, right? And I also try to run this one here. Yeah, so it seems correct, and I have verified that. Yeah, so that's it for this problem. You know, this problem I know it's just like you just need to find the those starting state that will make the first person always lose. You know, which we have like 4 special cases, right? And it 1, 2, 3, and 4. So you just need to find a way to check those 4 cases. And after that, since 2 players will both play optimally, so in the end, the next person will lose is like this. It's like a 0, 0, 1, 2, 3 until n minus 1. And then we just need to find the moves before reaching that. And then we can just uh, get the answer by the parity of the moves. Yep. Okay. Thank you so much for watching this video, guys. Stay tuned. See you guys soon. Bye bye.